we described this so-called optimal transport problem, sometimes called Monge-Kantorovich problem, right? So Monge-Kantorovich. Okay. And last time we didn't have time to discuss existence of the solution, and but the focus today will be on learning some basics of linear programming, okay, which is very fundamental to this course. Okay, so for existence of solution, we may have some time to consider later, but today let me be very brief that optimal solution of the optimal transport problem. By the way, do you remember the problem itself? So it is you want to minimize which objective function. I mean, so in optimization problem we have objective function and decision variable and constraints. Okay, so tell me what are these? So first, decision variable, transport plan. But to say about transport plans, we need some given information. What should be that rules? Mu and nu. So we have given mu and nu, just measures, but we have to have the same total mass in our formulation, so we assume they are probability measures. Okay, we want to consider this problem. We consider the transport plans, let's say pi between them. So the notation is like, okay, I have this big pi and mu and nu. Okay, the pi is a transport plan. That's our decision variable, and the constraint is already here, namely, the transport plan has these two marginals. So if you in x, if you take projection to x, then you have mu, and if you project it to y, then you have mu y. So here, what is hidden in this expression is that it is integration of pi xy, but only in y. So the result is a function of x. Likewise, here you have pi xy, but integrating x, you get function of y. So this is like projection to x and y variables. Okay, so for that projection, you should satisfy these given marginals. And then these are transport plans between these two given marginals. And our objective function is, so you first need to consider cost. So not only the mu and nu are given, but also the transportation cost function is given. It's like a function defined on the XY product space. And sometimes it may have infinite values. Okay, so we are given the transportation cost function, and then marginalize mu and nu, and then now we can fully write down the Monge-Kantorovich problem is minimization of among all these transport plans of the total cost, which is given by the integration of this cost function with respect to this transport plan pi over this product space x times y.
I have a question.
Yes.
Do we have any constraints on which cost functions we can use?
Oh, basically no, but to have some rich theory, you have some conditions. I mean, if you just consider, let's say, cost function is just constant, then this problem is trivial, right? Or non-interesting.
Right.
And then, so at least a cost function has to be non-trivial to have anything interesting. And then to have some rich theory, I mean, you need some kind of structure on the cost function, right? So maybe you want some kind of continuity at least, and then there are some other structural conditions given on the cost function. mimicking the properties of, let's say, the distance function or distance squared. These have some nice structural properties, okay? And
Okay.
having that, we can develop some nice theory. That's what happened during the last, I think, 30 years, okay?
Okay, thank you.
All right, so then the question is whether such, oh, by the way, we learned that, do you remember that given mu and nu, you can always find a transport plan, right? Am I right? So this problem is feasible. So you can always find a feasible solution, meaning a transport plan high satisfying these conditions. Okay, so the problem is feasible. Then, I mean, the problem feasible means there are some transport plans satisfying these conditions, given the constraint, but that doesn't necessarily mean we have an optimal solution, okay? Right. So feasibility is necessary condition to have any optimal solution, but that does not necessarily mean we have optimal solution, right? Okay, then the question is whether such a problem has an optimal solution. So that's what is in, not in this theorem, sorry. I chose the wrong, yeah. I mean, of course, this slide is necessary, but I want to just discuss it here, okay? All right, so this is the optimal transport problem. And the theorem says the following. Let X and Y be compact matrix space. Just assume that they are a compact space, basically. You don't even need matrix space, just compact. And then mu and nu, okay, so to say Borel probability measures, you need matrix space. But just don't worry about this Borel or matrix space. Okay. You have some probability measures. Okay. Sorry, okay, I need Borel. Okay, sorry, because I want this. So, and C is a continuous function on this. So here, so X and Y have some topology, and then C is continuous with respect to topology, and then you have this Borel probability measures, which is measurable with respect to Borel sigma algebra. Okay, whatever they are just terminal. For now, you can just treat them as just terminology if you are not familiar with this. You just treat X and Y be, for example, compact domains in Rn, okay? And mu and nu are just the Lebesgue measures, okay? Not just Lebesgue. Yeah, Borel measures mean just the measures, the natural measures on Rn, and then C is a continuous function. Then if you had this, basically continuity and compactness, then you can solve the de-optimization problem in this case, okay? Then you have solution, okay? Question?
Yeah, I have a question.
Yes.
So here, you said C is a continuous cost function, means that C cannot take infinite values, right?
Yeah, at the moment, because it's compact space. Yeah, so then.
Okay, I see. Yeah, thank you.
Other question? Okay, to give a proof of this such a theorem, we need to discuss some topology on the space of measures, okay? Which is called weak star topology. But let me not discuss this for today, okay? But basically, I mean, you can just believe that there is a very natural topology on the space of measures, okay? And if the domain, the underlying domain, in our case X and Y, are compact, then the space of measures on that domain with respect to this natural topology is again compact. Okay, so that is something you can just remember. Then then this space is compact. Okay, the space of transport plane is a space of measures. It's kind of closed set in the space of measures. So it's a compact, and you have this continuous function. So the integral is continuous. So you have continuous function, the cos function, which is a function of pi, the continuous function on compact space. So you have a minimum point. That's basically what it is. Okay. All right. So then existence is done for now. And one comment is that these conditions can be relaxed. So you can, for example, consider not just compact domains in Rn, but you can also consider the whole space. Okay. For example, also you may consider sometimes discontinuous cos functions, like cos functions, like I don't know, 0 up to some point, and then something like this. Or this is continuous. Sorry, something like this. Yeah. You may consider that kind of cos functions. Okay. But the theory is well developed under this condition, continuity of the cos function. All right. Okay. Now, the main topic today is to learn linear programming, which should be called linear optimization. Okay. So linear programming is not like writing code. Okay. So optimization in general is not just about, I mean, what we discussed before. You have decision variable, constraint, and objective function, and you want to optimize. Okay, and what is linear programming? In linear programming, the constraints and the objective function are all linear. So objective function being linear is that this function as a function of x is a linear function. So this decision variable x belongs to some vector space. Okay. And then you have a linear function. And the constraints it's not like, let's say, a linear space. The constraint as a set is something that is defined by linear equations and inequalities. Okay, that's what I mean. They're linear constraints. For example, optimal transport problem, let's say in discrete setting, here pi ij's are the transport plane. So here you have 1, 2, 3, like n for I, and then 1, 2, 3, n for j. Okay, and then you have the product space like these points, right? And then each point has pi ij value. So pi ij to find how much mass is over at each point ij. So pi ij is a transport plane, and it's a decision variable of this problem. And the constraint is that the marginal conditions are like if you consider that this projection to x, you get mu, and projection to y, you get mu. That's a constraint, and pi ij measures, so it's not negative. And then the function is this, basically this is integral, but in this case, it's just summation. So Cij times pi ij. Okay, so these are all linear expressions. So linear. This is not linear equation, but linear inequality, right? The linear function, the linear expression on the left, just pi ij, and bigger than or equal to 0. And this function is a linear function. Okay. So optimal transfer problem is a linear program. Okay. Okay, let's consider something important about linear programming. So to understand linear programming, you want to understand the geometric feature, okay, of such a problem. And let's discuss it in the finite dimensional case. So our decision variable, let's say, is in RD, d-dimensional space. Okay, so this is not the typical optimal transportation problem, because in our case, our decision variables are transport planes, right? And transport planes are measures, and then space of measures is like infinite dimensional space. I mean, space of measures is even bigger than space of functions. In some way, space of signed functions, right? So it's a much bigger space. So it is really a highly infinite dimensional space. But just for our discussion, let's just consider first this finite dimensional case. Okay, and then to consider linear expressions, you can consider a coefficient matrix. Okay, and B and C, B is a vector, and C is just a constant vector. Okay, so here, so this problem can be written as this maximizing. Okay, you can consider minimization problem, but let's just consider maximization for this case. Because if you open a textbook in linear programming, they mostly consider maximization problem. So that's why I also follow this maximization, even though our problem is a minimization problem. Okay, how can you go back and forth between maximization and minimization? You just take the opposite sign of the objective function. Then the maximization problem becomes minimization. Minimization problem becomes maximization. Okay, so this is like C1 x1 plus C2 x2 plus C d xd. Okay, that's a cost function. Sorry, the objective function, and then you want to do this in the constraint, right? Some linear expressions. First of all, x1, x2, all these decision variables are non-negative. That's the constraint. Also, you have other constraint like a11 x1 plus a12 x2 plus a1b xb is less than or equal to b1, a12 a2 1 a21 a21 x1 plus a22 x2 a2d xd is less than b2, and so on. So a k, we have a k such constant, a k1 x1 plus a kd xd is less than bk. Okay, so this expression is simply this expression. You want to maximize this dot product subject to that ax. So this expression comes from this matrix times this vector x, that is this expression, and b is here, this vector, and x being non-negative is here. Okay, so here C transpose is just transpose. So you can treat vector as a matrix, right? Just one row vector as a one row matrix, and then column vector as just one column matrix. Okay, then for matrices you can transpose, and then the dot product C dot x is the same as C transpose times x. Okay. It's easy computation. So this is the dot product, and what is this notation? Here x and this ax are vectors. B is also a vector. Between vectors, what is this inequality? I mean, vectors are not necessarily numbers, right? So how can you compare these vectors, and then what is this? What does this inequality mean? Here, let's say this x vector being non-negative means each component is non-negative. Okay, and here we have this vector a times x on the left, and the other vector b on the right. Then what is their comparison? You say that two vectors are in this inequality, if each component, like A is less than B, if A1 less than B1, A2 less than B2, so on. Okay? If each component has satisfied the condition, then you can just simply write down these conditions as just this simple expression. Okay, so in linear programming, they use this convention. Okay, maybe you don't see it in other areas of mathematics, but in linear programming. Okay. Okay, now, so this is a typical linear programming problem. Of course, it's in special form. Okay, so linear functions. Okay, I mean of course, when I say linear functions, I include linear function plus some constant. Okay, you can add some constant plus I don't know, like e or constant value. Still, I mean it's okay in linear programming. Okay? And also these expressions can be different, right? I mean, why do we have to have all these directional inequalities? Sometimes you want these inequalities, right? Or mixture of them. Okay, or the same here. Or even you may want some variable being negative or even without such condition. Okay, so there are more possible expressions of linear programming problems than this. But the thing is, all those problems can be translated into this form after some appropriate operation. Okay, so I'm not going to discuss that. Just the point is that this is the problem you want to solve. I mean, of course, every problem can be translated into this form in finite dimensional case. Okay. So that's why the textbooks in linear programming focus on this expression. All right. Okay, then you want to understand the geometry behind such a problem. Of course, the geometry of this object function is easy, just a linear function. So what kind of geometry do we want to consider? Let's say the functions have level sets, the set where the value is constant. Okay. So for this linear function, what is level sets? Let me repeat. Level sets are the sets where the value of the function is constant. So you have a level set for the value, let's say 1, level set for value 0, level set for value million, level set for value -2, and so on. Okay, so for linear function, what does that what do those level sets look like?
But hyperplane?
Yeah, they are hyperplanes. They are just we are in a d-dimensional space here, and the function is a linear function, and this linear function has its gradient. Okay, the direction where it increases most rapidly. What is the gradient of this function? Yeah, c is the gradient, right? For this linear function, the coefficient is the gradient, and then the level sets are something orthogonal to the gradient. Am I right? Remember your multivariable calculus. Okay. And then, but the gradient is just constant. So the orthogonal one, it's just an orthogonal hyperplane. And then these hyperplanes have, depending on the value of this c dot x, these hyperplanes have different locations, but they are all parallel because they all are orthogonal to the vector c. So here, the level sets of this function is a function of x. First, you have c, the gradient, right? And then the level sets are all orthogonal to this vector, okay? Of course, this is just a 2D case, but you can imagine in higher dimensional space, you have, let me just try to draw something like this, RD. Okay, it's not like 3D. Then you have instead, let me just try to make it more. You have instead some kind of plane like this. So do you understand my illustration? Am I making sense? Or maybe I shouldn't, let me be more. I want really parallel one, so let me just do that. These are parallel ones, and then no. Okay. Okay, so these are reverses of the objective function. Then what about the feasible set? First of all, you have, let's say, x bigger than or equal to 0 as a vector, and ax is less than or b as a vector. Okay. So these conditions are like x1 bigger than 0, x2 bigger than 0, so on, and a11 x1 plus a12 x2 a1k a1d a1d xd is less than b1 all the way to a1 x1 plus a2 x2. Okay, I'm just copying this thingy. Okay, now just let's pick this, because I mean the feasible set satisfies all these conditions, meaning all these inequalities. Okay. In other words, if you pick each of these inequalities, then each inequality gives a set, and then you have these other inequalities. So you have these other sets. Then the feasible set satisfying all these constraints is nothing but the intersection of the sets corresponding to each inequality. Am I making sense? Right? And then what does the set corresponding to each such inequality look like? For example, this one. Yeah, it's like maybe I think I need to draw only a 2D type picture. Okay, if this is x1 direction, then this set looks like this half space. Okay, so each of, and likewise this one also, they are all like, I mean, x2 is something like this, and x3 in higher dimension, right, like that. So the point is that each one is correspond to a half space. Okay. The same for these inequalities. Okay. Here, these inequalities, like let's pick this one. That one has that on the left. This is nothing but the dot product between some a vector and some vector coming from this a11, a12, a1d, and then you have this x1, xd. This is that dot product. It's less than p. Okay, and this dot product as a function, it has gradient, right? So it has some gradient, a11, a12, a1d. It has gradient, and it has corresponding level sets looking like this kind of hyperplanes, right? But then this condition that the value is less than or equal to B1, then the corresponding set should be what? So you first pick the equality case. Equality case is a hyperplane. Okay, so this is hyperplane. For the equation, this A equal to B1. Okay, and then the full set is those x satisfying this less than or inequality. So what should be such a set? Yeah, exactly this one. So this is a gradient direction, and this is a hyperplane giving this equality. So if you have this less than equality, then you choose the opposite space to the gradient. So that's why you get this half space, or the inequality. Okay, am I making sense? Okay, maybe I want to zoom out. So each such inequalities gives on half space. Okay, every such inequalities. Now the feasible set is the intersection of these sets, these half spaces. So as an illustration, let's just consider a 2D case. I hope this is not too trivial for you. Maybe not, because you're not answering my questions quickly. Okay, so in 2D case, you have, let's say, you may have some half space like this, and some other half space like that, and you have some half space scalar like this. And for example, if you have these 3 half spaces, then your intersection should be something like this. Or maybe I want to consider more. Okay, let's consider some half space like that. And then I'm running out of color. Okay, blue. And some half space like that. Okay, then the resulting space, the intersection will be like, it's challenging. This. Okay. So what can you say about such intersection? Yeah, so it's kind of, so in 2D is a polygon. It's exactly a polygon. So in high dimensional case, the corresponding object is called polytops. Okay, some kind of high dimensional version of polygon. Okay, so polytops have some kind of faces and edges and vertices and so on. Okay. All right. Not necessarily. Yeah. You can have something like this. Yeah. Yeah, it depends on their convention. Okay, in particular, the feasible cells satisfying this constraint, depending on this matrix A and this vector B, may not necessarily be bounded. Okay, they are unbounded feasible cells. It can be empty sometimes. Okay, or it can be bounded and then it's like polytope, but it can be like unbounded polytope. Okay. So, so that's the basic feature of the geometry of the feasible set and then the objective function. So then can draw like this way. Let's say Z is just represent the objective function. Let me a bit. Then this base is like RD. Okay, our like domain of the decision variables. Then the objective function is a linear function, so its graph in this space is like some kind of d-dimensional hyperplane. D-dimensional the graph of C dot X is a d-dimensional hyperplane, okay? And then you have this underlying, in the underlying set, you have the feasible set looking like this polytope, okay? Then you have, let's say, those level sets. And let's say this is the gradient direction. In this case, C. Okay. Then you can see that in this case, if you do this level sets, you consider level sets, then there will be this point having the largest value. Okay, so that's the optimal solution. Okay, so in linear programming, basically we have this picture, and then once you understand this picture, you immediately see that optimal solutions, at least a vertex is an optimal solution if it exists. Okay. So basically, linear programming is to find, it's about finding such a vertex, the optimal solution. Okay. In a finite dimensional case, okay. In infinite dimensional case, I mean, there are a few ways to having infinite dimensional case. Even when the decision variable is in finite dimensional space, you may have infinitely many constraints, right? The infinitely many half space to intersect. For example, you may have some kind of like this round shape, okay, as an intersection of infinitely many half spaces. Okay. Yes. Yeah, of course. You may, if the gradient is treated a little bit like this, then you have this level set, and the whole this let's say face of the polytope is optimal solutions. No, you have vertex, but you always have vertex as a solution, but not only vertex. What? Yeah, you may have you will have several vertices and the corresponding face. Very good question. Okay. Yeah, so I mean, maybe to the people in the Zoom, he just asked whether it's possible to have not just one optimal solution, but many optimal solutions. Yes, possible. You have some other, I mean, depending on the gradient, C, you may have the level sets just parallel to this face. Then this face is gives the optimal solutions. Then you have, like, in this particular picture, you have just two, but you have more two or more vertices as optimal solutions, but also any interpolation between any linear interpolation between those two vertices, like basically this face. Then, so in linear programming, you will have you can have no solution, or you can have only one solution, but you cannot have only two solutions. Okay, either 1, 0, 1, or infinite. The number of solutions. Okay, and of course, I mean, you can then there are other cases of infinite dimensional problem, like you have infinitely many decision variables, like in our optimal transportation problem. Typically, like the space of measures is infinite dimensional. Okay. Yeah, so that's what I say here. So in our problem, let's say if you consider x and y as open sets in RD, then you have x variables and y variables that are infinitely many such values, right? And then the measure over this space, the space of measures on such open sets is bigger than the space of functions. So it's highly infinite dimensional. Okay. Yeah, that's the point of this slide. The typical problem we will consider in this course is highly infinite dimensional. It's uncountably infinite dimensional. Okay. But still, I mean, this picture helps. Okay, question from the audience, I mean, the Zoom. You have to speak up if you have any questions, because I will not read your chat comment. Okay. All right. Then let's move on. Okay. Now, in linear programming, probably the most important and non-trivial concept is duality. And in my opinion, duality is also probably the most fundamental feature of optimal transportation. Okay? And some people may not agree. I mean, like 15 years ago, or even longer, when I started doing the research in optimal transportation, I kind of ignored duality because I just didn't like kind of abstract notion. I want to be more concrete in doing some problems, right? But then I was completely wrong. So okay, I could write some papers, but I think it could be much better if I really studied duality at that time. Okay, later, fortunately, I was forced to learn duality. Okay, then everything was different after that. So that's my advice, that this duality may look like abstract nonsense, but it's really not. It's really the core of optimal transportation theory, in my opinion. Okay, it's really important. And then if you understood duality, then I believe you will think in that way, and you cannot escape from thinking about it while doing optimal transportation. Okay, what is duality? in linear programming. It came from linear programming. And actually, the Kantorovich, one of the founding fathers of optimal transportation, is a creator of this notion, duality. Okay, what is it? So you have this linear programming problem. Okay, the duality says there is actually a companion, his friend. Another linear programming problem. Okay, when your original problem, which we call primal problem, was a maximization problem, then its dual problem, its companion, is a minimization problem. Okay, and of course, and you have different decision variables for the dual problem. Okay, so basically, dual problem is a problem in different world, in dual world. Okay, all right, and then how these objective functions and constants are related to each other. So here, the vector C defines the objective function. Okay, but now this C in the dual problem is here. It is something defining the constraint. Okay, and this B was a vector used in the constraint in the primal problem, but in the dual problem, this B is the gradient of the objective function. Okay, and this A was the coefficient matrix for the constraint in the primal problem. And in the dual problem, you use A, okay, but not exactly A, but A transpose. Okay, and you have this less than in. Okay, you keep this non-negativity in the dual problem for the decision variables, but for this part, this less than inequality now becomes now in the dual problem. Instead is greater than or equal to inequality. Okay, so things are similar but kind of the opposite. Okay. Okay, so in this slide, we just consider the finite dimensional finite cases like X is in like ID. Okay, and D is okay. Okay, just first accept that there's such dual problem. Okay, I will explain why you have such a dual problem. Okay, how come how do we come with this such a dual problem? So we'll explain that. But before that, first these three theorems for the relationship between the primal problem and the dual problem. Okay. The first thing is a so-called no duality gap. Sometimes it's called a strong duality, but I prefer this name, no duality gap. It's the following. If you examine these expressions, it is very easy to see that you have this inequality. That, I mean, the maximum value of the primal problem is always less than or equal to the dual value of the minimum value of the dual problem. Okay, this is something you can easily see. Okay, once you have like I don't know 5 minutes. But then this is not a theorem. It's a theorem by CG theorem, but the more non-trivial theorem is that it's not just inequality, but actually equality. The two values are equal. So there's no like strictness in the inequality. So there's no such gap. So that's why we call it no duality gap. They're equal. The maximum value of the primal problem and the minimum value of the dual problem are equal. Okay. This is first important theorem for duality. And second, oh, by the way, I mean, of course, this holds when only when these problems are feasible, right? When the both problems are feasible, we have equality. Not only that, in fact, you have optimal solution of both problems. Okay. If both primal and dual problems are feasible. There are cases where primal problem is feasible, but dual problem is not. There are such cases. Also, dual problem is feasible, but the primal problem is not feasible. Also, even both primal and dual problems are not feasible. Okay, I'm not talking about these cases. So, but in the case where both primal and dual problems are feasible, then there's no duality gap. Not only that, both problems have optimal solutions. If you just consider one single problem, feasibility of the problem does not necessarily mean that that problem has an optimal solution. Okay? But if both dual problem, primal problem and the dual problem are feasible, then they both automatically have optimal solution. Okay? At least in this finite dimensional case, right? And then the third theorem, called so-called complementary slackness. The name sounds funny. Appreciate this name once you see the explanation. So it just says that the primal problem and dual problem now have optimal solution when they are feasible, and their optimal solutions have very nice relationship between them. Okay, it's not like okay, you can find an optimal solution for primal problem and optimal solution for dual problem, but they are kind of random. No, they are closely related. In a way, if you know the optimal solution of the primal problem, you can characterize the optimal solution of the dual problem. If you know the optimal solution of the dual problem, you can characterize the optimal solution of the primal problem. Okay, so this feature turns out to be very important in optimal transportation problem. Okay, why? Because you will learn later. In optimal transport, primal problem has decision variables that are measures, right? Okay, but then can you guess what decision problems? So what decision variables the dual problem to optimal transportation has? So in optimal transport, primal problem has decision variables that are given by measures. Measures are the variables. Okay. So if you consider the dual problem, then what should be the dual decision variable? What? Dual measures? Maybe this is something you already learned in your in your real variable course, real analysis course. What is due to functions? Okay, just functions. Okay, so the dual variables are functions in optimal transport. Okay, then this complement slackness. So dual solution will be some functions. Okay, and then, but they should satisfy some conditions because of this constraint, right? And these conditions for the dual solution will give us some actually partial differential equations. Okay, and then the solution satisfies some very special feature. And then through complement slackness, the solution to the dual problem will characterize the solution to the primal problem. And this is the way how we connect PD theory to optimal transport. Okay, you will see this more later. Okay. So these are three key theorems of linear programming. Okay? Node root gap, attainment, and complement slackness. And they will be three key theorems of optimal transportation too. Okay. All right. Okay. Now let me explain where this dual problem comes from. Okay. So there could be many ways, but one expression I like is to consider so-called penalty method in constraint optimization. So you have this constraint optimization problem. You have objective function under this constraints, but then you can turn this constrained problem into unconstrained problem. Okay, but you have to modify your objective function. Okay, how? You just add a penalty term to your objective function. Namely, if your variable satisfy the constraint, then no penalty. If your variable does not satisfy the constraint, then you have infinite penalty. Okay, so this is maximization problem. So you put penalty negative infinity. All right, it's like this. You want to maintain safe safe driving conditions on the road. Okay, you are like a police station. Okay, who wants to enforce, who wants to maintain safe driving conditions. Okay, then you have speed limit. So this penalty, I mean, it's like you want to maximize something under the condition that the drivers satisfy the speed limit. Okay, and then to achieve that, you can do the following. So when they violate the speed limit, okay, you charge, I don't know, I mean, the infinite amount of money. Then nobody will dare to violate the speed limit, okay? The reason why there are many drivers who violate the speed limit is because the penalty is so low. The expected penalty is almost zero, right? So that's why. But anyways, that's the penalty method. So you can turn this constraint problem into unconstrained problem while modifying or adding the penalty term into your original objective function. Okay, am I making sense? Right. Okay, but this is super uninteresting, right? Just this is like, I don't know, it's like kind of tautology, or I mean, we didn't make any progress. So we just say the exact the same thing in different way. But this gives us a very new viewpoint to the problem, right? So then what we can do is, okay, maybe this infinite amount of money is not realizable, right? It's like a death penalty almost. So it's not realizable. So you make a little bit soft penalty. Okay, instead of charging infinite amount of money, you just charge some fine, right? Gradually. If you violate, let's say 5 kilometers over, then you charge like $50. I mean, 10 kilometers over, you charge $100 and so on. Okay, that is like soft penalty. Okay, so instead of this kind of simple function, you put a function which gives some penalty value, but depending on how much you violate the condition. Okay, so here in linear programming, you can put this kind of linear penalty function. It's a function, it's a linear function in X. Okay, A is the matrix, this matrix, and B came from that. So here, what it is? If this value is, and then this y is a coefficient vector. Y is just some fixed vector. coefficient vector for this expression. So this is just dot product y dot b minus ax. Okay. And then what does it do? And w the same. It's a coefficient, but they are non-negative. So if your x is, let's say, less than something, like xj is less than something, then you will get some negative value for this. Likewise, if b minus ax is less than some 0, then you will get negative value for this. Okay? So it is like a penalty. And the more you violate the other way, yeah, you violate this condition, the more negative value you will get. But this is a linear function, so if you satisfy more your constraint, then you will get even reward. It's not just penalty, but also reward. Right? So if you drive like 5 kilometers under, then the police station will pay you, I don't know, $5, something like that. So this is a soft penalty, but also it can be a reward if you satisfy the constraints. Okay, and here these coefficient vectors have a really important name. They are called Lagrange multipliers. Okay. Yeah, this is the Lagrange multiplier you learned in your calculus course. All right. Okay, then how this penalty method is related to duality? Okay, now, so instead of the original constant problem, which can be translated into this unconstant problem with this like infinite penalty, or sometimes we call it hard penalty. You consider this soft penalty problem with the same goal of maximizing, but you just have this slightly different objective function. Okay, so this problem is not exactly the same as this problem, but it can be related. Here, given and w, given Lagrange multipliers y and w, you can consider the maximum value of this. Okay, like a total benefit of putting this, let's say, soft penalty.
Younghan, is GYW the same as PYW?
Oh, sorry. It's a great comment. It's a P. Thank you. Right. Oh, by the way, just I forgot to mention this. These Lagrange multipliers are like this. So these are the rate. So if you violate like 10 kilometers, then how much would you charge? Like $10 or $100? So what should the rate of charge? Okay. So then, depending on the rate of charge, you may have different results, right? If your charge is, let's say, very high, then everybody will slow down, right? They don't want to violate the speed limit, and because it's even reward. And the charge is high, then you want to slow down. You want to drive very slowly, then you will get paid by the police very highly. But then the police doesn't want it, because not only they have to pay a lot, but also the traffic condition will be even worse. Everybody's drive slowly. It is not good. So let's say this maximum value is kind of the total benefit to the community for setting up such traffic fines, okay, the rate of charge. And then there will be some optimal such values for the rate of charge, right? Achieving the best such value. Am I making sense here? Okay, am I making sense? Okay. Okay, but one observation is that this value for any y and w, non-negative, this value is always bigger than or equal to the original maximum value of the original problem. Can you see why? Yeah, so let me just repeat what he said. That's exactly what I wanted to say. If your x is satisfying this constraint, then there the penalty term is not even a reward, it's a bonus. So the objective value is even bigger than or equal to this value. So if you satisfy, then the maximum value will be bigger than or equal to this maximum value, right? Am I making sense? So that's why you have this. But then let me back to this police station example. So each rate of charge, you have some total benefit to the community, right? But then you want to get, you want to make such charge as much as possible that the result will be the same as the original concept, the original problem. Okay, am I making sense? All right. But this value is always bigger than or equal to. So to achieve our goal to make this choice of this rate of charge in such a way that the result will be as close as to the original problem, then what should you do? You want to make this value as close as possible to this value. Then to do that, what do you want to do? You want to, yeah, as she said, you want to minimize this thing. Now the decision variables are this rate of charge, y and w. Okay, so that's why you want to consider this. Okay, am I making sense over the Zoom? Because I cannot see you over the Zoom, so maybe sometimes you want to make a comment or some reaction.
I think it makes sense. Thanks.
Okay. Good. Okay, then what happens if you do this problem? By the way, this problem is not exactly a linear problem, right? Because the function is not linear. This function is not linear. So given y, w, you get this maximum value. This is not linear. Okay. Even though here the expressions are linear. It's a linear in y and w. This is a linear function inside, but you maximize over x. So this is not linear. But can you, do you know what kind of function this is? If you maximize over some family of linear functions. So for each x, you have linear function. So this is a function of y and w, but for each x, you have some linear function looking like that. Yeah, and then for other x, you have some other linear function looking like this. And for other x, you have some linear function looking like that. And now, and for other function, you have some linear function looking like, I don't know, like this, okay? The graph. Then if you maximize over all these different x, then you get, in the end, you get some kind of this part, this part, this part, this part. Okay. Imagine you have infinity such many such functions. Then you will get the maximum over or supremum over all these. So the resulting function should be, yeah, this is a convex function. Sup of a family of linear functions is a convex function. So every function, convex function is like this. It's a soup of linear functions. Okay. So this is about minimizing a convex function over a certain feasible set. Okay. Okay. Now there are a few exercises. Why am I too slow? Regarding this, I think you want to do all this, okay? Yeah, let me just leave it for you. Then, if you do this step-by-step exercise, then first, this problem, we want the minimizing this convex function over this rate of charge y and w, turns out to be this now linear programming. You can turn it into a linear programming like this. Okay. That is, these steps are explained this. Okay, you can do this. And then this linear programming, you can also turn into this problem, which was our dual problem. So this problem, minimizing the rate of charge of this soft penalty modified object functional value, objective value, is the same as the dual problem. So dual problem, it just find some optimal rate of charge for your penalty. Okay. Yeah, please do these exercises. Okay, then I have 5 minutes. Then here, remember, this value is always bigger than or equal to this value, max, the original problem. Okay, and no duality gap says this value is actually equal to that maximum value. That's what no duality gap says. Like this. Okay, and why do you have such a relation? And let me explain this shortly. Here, remember, this problem is the same as this. I just expressed this in full. This is the penalty function, our g y w x p. Okay. And then this is first you maximize over x, and then later you minimize over yw. Okay. But now, in fact, you can change the order of this max and min. Okay. So this is like very important theorem called min-max theorem or minimax theorem. Important names are associated to it. For example, von Neumann and that in our setting, this finite dimensional linear problems, you can do this max min shuffling. You can exchange the order of max and min. This is called min max theorem. Then once you do it, then let's now see this. So you want to minimize over y and w. Then this minimization applies only here and there. Okay. Now, that is this step. So if you consider the minimization of this, what happens? Here, do I want to okay, I think I want to explain this. You want to minimize. suppose this is violate. I mean, the original constraint says AX is less than B, but suppose this is negative, so AX is bigger than B. Then for your Y, you can choose, there's no other constraint than non-negativity. So you can choose infinitely large Y. Oh, sorry, it's minimization. Oh, I'm sorry, it's a minimization. So you can choose, yeah, infinitely large Y. Then it will be smaller and smaller. Because it is negative, the value will be negative. So this minimum will be negative infinity. But after that, you want to maximize. But you already get negative infinity. So your maximum value will be negative infinity in that case. So this will not be maximum value, right? The ultimate goal is to maximize. But if your X does not satisfy this non-negativity, if some component is strictly less than 0, then you can, your Y for the corresponding component to your Y can be like infinity, then you will get negative infinity value. So it does not give us a maximum solution. So you can ignore such a case. So you can ignore the case where this is negative. Likewise, you can ignore the case this is negative. Because there, this minimum value will be negative infinity. So you did not give us any maximum value. So for this maximization problem, you can ignore those cases that violate the original constraint. So that's why this problem is exactly the same as this problem. And why? Okay, you can ignore those. Now, once you satisfy this is non-negative, this is non-negative, then the minimum value of this problem will be 0, right? Because you just want to put 0 for your Y and for your W. So if your constraint for X, the original constraint for X is not satisfied, this minimum value will be infinity. If the constraint is satisfied, the minimum value is 0. So you can just cancel this expression and you can put instead this constraint. And these two problems are equal. Am I making sense? That's why you have this. So that's why this dual problem is the same as, have the same value as the original problem. Okay. I'm too slow. Okay, so see you on Monday. So on Monday, I think I will explain. I think I can skip the meaning of this dual problem. You can just read it, and then I will explain probably the attainment and complement and slackness. Okay, I start.